after this insightful session. It's an absolute privilege to introduce our next special guest, a trailblazer who has seamlessly transitioned from skies to the seas. Hailing from Guntur, Andhra Pradesh, and a proud BITS Pilani alumni, Miss Padmini Mellacheravu's career journey is nothing short of remarkable. As a former engineer associated with cryogenic rocket systems at ISRO, she was instrumental in space exploration, but her passion for innovation took a pioneering turn when she shifted gears and joined Lloyds Register. Based out of their Southampton office, she has become a global leader in decarbonization efforts, playing a key role in writing the world's first-class rules for hydrogen-powered ships, an achievement that is shaping the future of maritime sustainability. This milestone, which supports the industry's goals for greener shipping, has earned her the well-deserved title of the Maritime Hydrogen Lady. By the way, this title is given by us at TNC. So despite the demands of her career and recently becoming a proud mother for just 4 months ago, Ms. Padmini graciously accepted our invitation to be with us today. Her story is one of passion, resilience, and commitment to making a difference. It is with great pride and admiration that I welcome Ms. Padmini Mellacheravu to the stage.
Good afternoon, everyone. Thank you very much for the invitation. So today, after this wonderful talk, I'm going to give some positive news, but also wrapped up in a bit of negative news, unfortunately. So let me give my topic. I'm going to talk about hydrogen systems. So I'm going to talk about the challenges and opportunities that hydrogen has in marine context. But before I go into that, I want to give a bit more introduction about what I do at Lloyds Register. So as you all know, Lloyds Register is one of the world's first classification society. So I'm a subject matter expert in hydrogen systems. What I do day in, day out is talk about hydrogen systems, share my expertise that I've gained by working in Indian Space Research Organization, shape the projects that are coming up on hydrogen systems. Why I'm expanding more on what I do is because what I am is more important than what I'm going to talk about. That is because here we are amongst stalwarts of marine industry, somebody who has more than 40 years of experience in maritime. So why am I, who only have just about 2 years of experience in marine, talking here? That is because I am the technology in maritime. The technology, the future of maritime is in alternative fuels. We have just heard about the talk. There is huge push towards net zero and zero carbon fuels, and hydrogen is one of the fuels that can achieve this net zero, especially for the shipping context. So that is why I'm going to talk more about hydrogen systems and what opportunities that you as student delegates have in the future or building the future of shipping industry. So I was talking about Lloyds Register. We offer classification and compliance solutions also as a trusted advisor, because hydrogen systems, these are new projects. Nobody knows for sure what is going to happen, both from a technology perspective and also from a techno-economic perspective. So we, Lloyds Register, are also offering advisory sources to share our knowledge, share our expertise on hydrogen systems and other alternative fuels to come up with innovative solutions and see what works for our marine industry. And also some innovative and digital solutions for fully autonomous ships, etc. So let us take a brief look about hydrogen in maritime. Like why are we even discussing about hydrogen? Why should we go for hydrogen? Simple answer is IMO's strategy to reduce greenhouse gas emissions. We have seen a lot of greenhouse gas emissions from all the industries. Shipping alone contributes to around 3% of GHG emissions. So there is IMO has strict policy to reduce these emissions by at least 50% the time 2050 comes around. And 2050, let me remind you, is not far away, because it's less than 30 years from now. And shipping industry builds ships for more than 25 years. So any ship that is being built today has to be compliant to this, otherwise it will be a wasted asset by the time 2050 rolls around. And there is also a goal for 2030. So anything that is under construction or already in service now, if it is not zero carbon or net zero carbon, it is not going to be useful by 2030 or 2050. So the solution and the implementation has to be today rather than someplace else in the future. So there are several alternative fuels. So it's not just hydrogen. So this hydrogen is one of the solutions. What others do we have? We have ammonia. Ammonia is a very good alternative fuel. It's zero carbon, but there are challenges with ammonia. Ammonia is highly toxic. So I'm not going to go into too much detail about other alternative fuels, but ammonia has a toxicity challenge which is hindering its implementation into marine industry. Biofuels are really good. On paper, they are the best fuels, alternative fuels that can be used for any sector, but unfortunately, the availability of biofuels is very less. So the amount of fuel we need thousands of metric tons per day, and there is not much biofuel being produced that can sustain the cyclic economy in marine industry. So if it were, it would be good, but unfortunately it is not. And coming to batteries, batteries are really good short distance shipping solution, but they become too heavy and less energy intensive as the distance or the weight category of ships increases. So they're good for small port to port, but once we go for higher amounts of shipping needs, batteries cannot be sustained because they become too heavy, occupy too much space compared to the efficient the carbon emission that they're reducing. So as we have heard in the previous talk, it just doesn't, the scale doesn't balance out when batteries we are using for higher power needs. So what is the solution? Hydrogen is one of the most promising potential zero emission solution, and done right, it can even be a zero carbon, zero net emission solution out of all the alternative fuels. And it can scale up to the amounts that shipping industry needs in terms of the energy carrier as well as fuel. So as I mentioned, while there are multiple solutions, hydrogen is one of the most potentially net zero or zero carbon fuel that is available for shipping. So how is hydrogen produced? 80 to 90% of hydrogen produced today is coming from fossil fuel as a byproduct of fossil fuel production. So it is termed as gray. There is a color coding just to indicate what is the carbon footprint of hydrogen. So while we are saying hydrogen is net zero, because hydrogen, when it just burns with oxygen and produces water. So that part of the equation is completely zero carbon. But as we have heard in our previous talk, the upper stream, what happens when hydrogen is being produced, what is a carbon emission footprint of production of hydrogen determines the color coding. So roughly we can say green or brown hydrogen is basically very dirty in terms of carbon production. So that is coming from extraction of hydrogen from fossil fuels. So there's a lot of carbon emission in that. Somewhat better is blue hydrogen. So what it does, during the process of hydrogen capturing, it's a byproduct. So we are not mining hydrogen, but the byproduct of steam methane reformation, basically production of LNG or cleaning up of the fuels. So during that process, if there is some carbon capture happening, so we are reducing the footprint while hydrogen is being produced, footprint of carbon dioxide while hydrogen is being produced. So this is termed as blue hydrogen, and around 10 to 20% comes from of hydrogen today that we are using for whatever projects we have, comes from this blue hydrogen source. Then comes the better alternative is green hydrogen or pink hydrogen. So green hydrogen is basically hydrogen produced by using electrolysis of water. So there is no carbon, again, from the previous talk, there is no such thing as zero carbon anywhere in the world. But from a net zero perspective, we are taking fossil fuels like solar, etc., using that energy in an electrolyzer and converting water to hydrogen and using that hydrogen for our purpose. So this is a net zero solution for hydrogen production. And if we are using nuclear instead of solar, that becomes a pink hydrogen. So these are one of the cleanest sources of producing hydrogen. And then this is the latest thing that has come up less than 2 years ago is white hydrogen solution. So in France, they have discovered reserves of hydrogen underground. So basically hydrogen can be mined like we mine other oil sources. So that is white hydrogen, and there's a lot of research happening in that. Apparently there are several thousand tons of hydrogen underground, which is ready to use. And if we are able to mine it in a sustainable way, this could be a really good solution for the future. So again, if we are able to produce either green hydrogen or maybe sustainable white hydrogen, it has the potential to become 100% emission free from well to wake. So that is entire life cycle process. Hydrogen has this potential when it is used in green or pink. So how hydrogen is stored? So hydrogen has most of the technology that we have, the most useful industrial technology that we have is using either compressed gas or liquefied gas. So compressed gas has to be at around 200 or 700 bar at normal temperature, or we can either liquefy it to minus 253 degrees centigrade to convert it into liquid so that it can be stored. Why we have to go for this, I'll explain a bit later, but that is to have the highest efficiency from the energy we have by carrying 1 kilogram or 1 volumetric unit of hydrogen. Then comes the next solutions. These are being researched. One is organic hydrates. So liquid organic hydrates are chemical compositions of hydrogen, and they can be either adsorbed into this, the material and desorbed from hydrogen. So this is one of the solutions which is coming up, and it is hailed as future solution because it takes out a lot of challenges that hydrogen poses. Then comes metal hydrates. Metal hydrates again are chemical compounds which has hydrogen captured in the metals, and they can be adsorbed and desorbed from the solid material. So these two basically are using, So these two are basically using chemistry to carry, transport and bring out the hydrogen by removing this inherent safety challenges that hydrogen poses. So these are the advantages, but these are yet to see large-scale implementation in the industry. There's a lot of research going on and very promising research. I'm sure that we will see most of it in the future, coming 5 to 10 years. So what do we do once we have hydrogen? How does it work out? So hydrogen can be used for energy production. So it can be used in fuel cells. So fuel cells and hydrogen go hand in hand because that can create the net zero emission. So fuel cells, there are several types of fuel cells. There's a proton exchange membrane, solid oxide. So they work on different technology. They have different pros and cons in terms of the temperature that they work on, the efficiency that they produce, and the temperature, wasted energy potential, etc. But the whole basket of fuel cells are very highly efficient when using hydrogen, and they have efficiency between 50 to 60%. And combustion engines, it can be used in combustion engines just like we use any other fuel. It is the best fuel, and the output is only water. But the challenge is hydrogen burns at very high temperature. So how do we take on this heat, the materials that can sustain this, and how do we protect our systems from this is the challenge. But a lot of engine manufacturing companies, all the major GT, everybody is working on hydrogen engine manufacturing. And by 2030, I'm sure there are catalogs that are going to come out for pure hydrogen engines. But that is far away. What can happen today is mixture. So even a 50% mixture of hydrogen in heavy fuel oil can reduce the CO2 emissions by up to 43% per ton kilometer. And with the current engines, LNG, there is no restriction on doing at least 20% of hydrogen. So we can directly take hydrogen, put it in an LNG engine and mix it up to 20%, and we can have a lot of carbon footprint offset by using this technology. So not just pure hydrogen, we can also think about blending solutions to reduce our greenhouse gas potential in shipping. But if hydrogen is so good, what is the problem? Why don't we already have hydrogen systems? What is stopping us from large-scale adoption of hydrogen? Challenges. The first thing that, when I say hydrogen, the first thing that you think about is probably a hydrogen bomb. And that is because hydrogen is a huge safety challenge. So the properties of hydrogen, the inherent hydrogen properties are the reason for this safety problem. The first is highly flammable. I know there are a lot of students here, so if you remember your fire triangle, there are 3 things that are required for any fire. You need a fuel, you need an oxidizer, and you need an ignition source. And hydrogen is really bad with all 3 of them. So hydrogen is the best fuel. So the way oxygen is the best oxidizer, hydrogen is the best fuel. And the capacity of hydrogen to burn in a mixture. So anything you take, pure hydrogen cannot burn. It needs oxygen to be able to burn. So the ratio of hydrogen and oxygen that is needed to sustain combustion is very high. So it burns from 4% to 75% in air. So even a very small leak, if it can come up to 4% of hydrogen concentration in the air, it will be able to sustain fire. So for comparison, other heavy fuel, etc., you need LNG, you need around 20%. So you need significant amount of natural gas to be able to burn, but for hydrogen, even a minuscule amount of 4% is sufficient to sustain ignition. So it's very dangerous, even a small amount leaks out. Another one is low minimum ignition energy. So as I mentioned, the third thing is ignition that is needed for fire. And for hydrogen, the amount of energy needed for the ignition to take place is very less. So that is, it can be ignited by electrostatic discharge. It is so small, 20 millijoules. So what does it mean? If I do this, this energy, the energy produced by friction of my fingers when I do this snap, that is sufficient to ignite when there is a hydrogen. So that is how dangerous hydrogen is, because it can ignite very easily. Whenever there is hydrogen leak, assume that there will be hydrogen fire, because anything can make it catch fire. Another problem, and we are thinking why I might keep on saying why hydrogen leaks, because it does. It is a very small molecule and it has very low density. So it is one of the smallest molecules, and hydrogen atom is the smallest. So only second to helium molecule in terms of size. So it has extremely high potential for leaks and easily disperses into the atmosphere. So when we are talking about plumbing, if we have a plumbing, nothing is safe against the leak of hydrogen unless we weld it. So anything that we have leak-tight joints, we have thread joints, etc., these are not hydrogen safe. So anything that is leak-tight for nitrogen, say, because nitrogen is a heavier or bigger molecule, that is leak-tight for hydrogen. It is not leak-tight for hydrogen. So we need to think of better engineering solutions to contain hydrogen. Another interesting thing is hydrogen, when it is burned, is colorless. So it's almost invisible flame. We cannot see when hydrogen is burning. So I was working in Indian Space Research Organization, and let me tell you, NASA's handbook to detect hydrogen still has one sure shot way of identifying hydrogen fire is to take a wooden broomstick, go along the piping, and whenever the broomstick burns, that's when you know hydrogen is burning. So it is that, it's impossible, so in some lighting scenarios, it is impossible to detect that hydrogen is burning. But it will burn at very high temperature, and high flames will be happening, but we cannot see it. That is because of the property. So in this scenario, from a naked eye, from a normal perspective, we cannot see that hydrogen is burning, and we wouldn't even know that hydrogen is leaking because we are not seeing any fire with naked eye. So because of all these properties, it is difficult to detect combustion, basically. So because of all these properties, it makes it a huge safety challenge to contain and transport hydrogen safely. Then comes design challenges with hydrogen. Material compatibility. So hydrogen has this property called embrittlement. Again, it comes from its inherent property of being very small. So hydrogen atom is very small. One of the ways in which it spoils a material, one of the common materials in marine is ductile iron or cast iron. So hydrogen atom goes and sits between the material or between the iron atoms and create hydrides. And basically what it does, it takes a ductile material and makes it into a brittle material, and the material fails in brittle challenge. So one of the most common materials, it cannot be used for containing hydrogen. You need better special materials such as SS stainless steel, that too austenitic stainless steel. These are all technical terms that I don't want to put here, but basically cost increase and higher engineering challenge. And when we go for composites, again, hydrogen is very small. So any hydrogen atom can easily pass through the composite because composites have more interstitial spaces between the atoms. So hydrogen easily goes out. So on some of the cheaper composites like nitrile rubber, they are not hydrogen, they are not safe from hydrogen. Another challenge for marine specifically is scaling up. So at present, the largest liquid hydrogen tank is only 4,700 cubic meters. And for marine, what is the highest LNG tank that we are transporting? It is 400,000 cubic meters. So there is 100 times scaling up challenge. And it is not just a tank building. I'm not going into the too much technical detail here, but for carrying out liquid hydrogen, you need vacuum systems. So you need a tank, and then you need an outer tank, and there should be vacuum in the space. Otherwise, the minus 253 degrees that is inside, it is not going to stay at that low temperature even for 5 minutes. So basically, you need like a thermos flask. But thermos flask is this, and we are talking about a huge ship, which is a thermos flask. That is what is needed for hydrogen to be in liquid form, and that's when it can be transported efficiently. Sir, next slide. Yeah, so why do I keep saying we need to go for higher pressure or lower temperature? That is again because hydrogen has very low volumetric energy density. So if we take per kg, hydrogen is the best fuel when we compare per kg. So 1 kg of hydrogen is much better than 1 kg of marine gas oil or LNG, etc. But if we take volumetric energy density, as in per liter, if I take atmospheric hydrogen 1 liter, it is very poor in terms of the energy that it has compared to 1 liter of LNG or 1 liter of marine gas oil, etc. So how does it compare? So for this to overcome, we need to compress hydrogen. We need to store more hydrogen in less volume, either by compressing it, and we need to be stored at very high pressures. I am talking about 700 bar, 1000 bars of hydrogen to be stored to have any semblance of a good fuel on board. Or you can go for liquefaction or cryogenics. So basically take hydrogen, which is which is a gas at ambient temperature, and cool it down to minus 253 degrees. So there is 0 Kelvin, which is absolute zero, and 20 Kelvin above that. We are 273 Kelvin above that. So 20 Kelvin above that is where hydrogen can be formed in liquid state, and use that liquid. And it's not just that we are making hydrogen, it can be that way. We have to maintain that low temperature throughout the usage life, which is maybe 10 days sometimes to maybe years, decades sometimes, that is needed to. So we need to maintain that at such low temperatures. So imagine the engineering it takes, the material engineering as well as the thermal and the stress loads, thermal engineering, everything required to maintain, design and maintain such systems. That too, remember, hydrogen leaks very easily. It is prone for fire. So everything is an engineering challenge. The design challenge is needed to get any amount of useful energy from hydrogen. And it also, because the impact of all this low volumetric energy density is it occupies more space on board. For comparison, coming from an LNG, if you have an LNG tank, to get the same amount of energy from hydrogen, you need at least 4 times the space needed for compressed hydrogen at 700 bar, or 2 times the space needed for liquid hydrogen. So even when we are going to minus 250 degrees centigrade, doing all the engineering and storing it at that temperature, you still need twice as much space as LNG to be able to get the same amount of. So I'm seeing all the shipping industry people with a dollar sign, like the dollars are falling, because it takes a lot of operation cost, it takes a lot of engineering cost, and again we are compromising on the cargo or passengers that are bringing in the money. So these are the reasons why hydrogen is not easily adopted. Again, there are some implementation problems. Regulations. So shipping industry is happily working on all the IMO regulations. There is a rule book for everything. There is IGF code, IGC code. People are happy with how everything is written down, so there is no problem. But nothing is written down for hydrogen or any other alternative fuels now. So IMO is still working on it. On the regulations, something is coming up. Some interim recommendations will be coming up soon. But at the moment, we don't have anything concrete to work for hydrogen, ammonia, or other alternative fuels. So at the moment, everything is based on approval of alternative design and arrangement. So what that does mean is there will be a bunch of experts sitting on the table, everybody discussing, tearing apart a design submitted by an owner, and we have to come up with solutions that are maximum safety oriented. Only then will we be able to approve, coming from a class society, only then can LR class that ship which has hydrogen. Because the onus is on the pioneers, the first movers and classification society who are supporting them to come up with the maximum safe hydrogen systems. Because once there is a failure, once there is a catastrophic failure, imagine nuclear. So because there were failures in nuclear technology, now nobody wants to immediately adopt nuclear. There's a lot of hindrance, there is a lot of confusion amongst nuclear. So similarly, we don't want failures or catastrophes to determine the future of this really good technology. So we are taking the moderate and conservative approach in terms of safety. But in the future, this will be reduced once we have more experience, more number of projects. We can cut back on the safety measures. I won't say safety measures, we can cut back on the existing technology and adopt more upcoming technologies so that we can reduce the cost. But at present, it's a huge hindrance from a techno-economic aspect to adopt hydrogen technology. Then limited industry knowledge and experience. So I started my presentation by saying I'm not from marine, I only have less than 2 years of experience. But why did LR go for me who have no maritime experience? That is because nobody in the industry has hydrogen experience. There are very few people who have hands-on experience on dealing with large-scale hydrogen systems. and very few are there, and most of them are only from land-based industries, nobody from marine. So there's very few people, so there is a lot of specialist crew training needed for upcoming people to make them happy with hydrogen technology. So people are not coming up to work with hydrogen technology, let alone working, training. So that is secondary. The first is people need to come forward to work with hydrogen. So this is one of the, I would say, call for invitation at the moment. There are a lot of student delegates here. I would encourage every one of you to go back, think about hydrogen or any other alternative systems, and plan your career towards alternative fuels, because that is the future of industry. So there's a lot of scope. I am coming from non-maritime industry, so if somebody can be able to understudy under me, they can learn about hydrogen systems, but you already have a lot of marine industry. So that marriage between this land-based technology and marine industry can bring on wonderful innovations, which I, coming from non-maritime background, cannot see. So even now when I'm sitting in projects and coming up with a lot of new projects, it's a learning day from me. I learn a lot about hydrogen, more than what I've learned in my 8 years of working with hydrogen. So that is how much innovation potential there is in maritime for hydrogen or any alternative fuels. So this is a call for invitation for all the students to look into this and plan your career in that aspect. There's a lot of future in that. So looking at this, now again you may be questioning, why hydrogen? This sounds too challenging, too dangerous. Why should we even bother about hydrogen? Because it is one of the better fuels that we can have. Then this is not a future, this is not a pipe dream. There are already projects in service which are using hydrogen as fuel. These are the early applications that I have. There's a hydrogen as fuel is being used by tugboats. There's hydro tug series. There are 4 to 5 tugboats which are using hydrogen as fuel running in Northern Europe. There are passenger ferries. There's cruise ships, which is with Orca, and several cruise ships in service and in building phase. There are bulk carriers, and there's even like luxury super yachts coming up with hydrogen. In very few years, you will be able to see news of all of them coming into service. They are all under construction at the moment. And there's also hydrogen as cargo in a LH2 carrier. So Suzo Frontier is a technology demonstration demonstrated by Japan, which has carried hydrogen, liquid hydrogen between Australia and Japan. So technology is there. It's just a matter of adopting it. So as I was asking, why should marine bother about hydrogen? Because as much as marine industry needs hydrogen to decarbonize, hydrogen itself, the decarbonization industry itself needs maritime to be able to transport hydrogen. Like we have seen in the previous talk, there are a lot of hard to abate industries. So we are talking about transportation sector, steel making sector, every other sector, everybody wants to decarbonize, but hydrogen sits in the middle of all of them. So if you take large scale renewable energy integration to power generation, so as we were mentioning, we can use solar energy and use that energy to produce hydrogen and use that hydrogen as a green energy source. It can be decarbonizing the industry heat utilization. It can be for renewable stock. It can be for decarbonizing heating and power for buildings, for transportation. These are all hard to abate industries which cannot be, electrical battery may not be a good solution for them. So all of them need hydrogen, and all this hydrogen has to be carried by shipping industry. There is no other way you can cheaply transport goods and services other than shipping. So shipping will be called upon to transport hydrogen. And most of the time it will be liquid hydrogen transportation. So even if shipping doesn't want to work with hydrogen, hydrogen will not leave shipping. So yeah, so this sort of is my conclusion, is there are challenges, there are engineering solutions. Everything is available. So hydrogen is new to marine industry. It's probably only like a few years old, but it is almost 50-year-old technology for land-based applications. Aerospace industries, cryogenic industries, they have been working with hydrogen for several decades now, and a lot of knowledge is already available. Whatever I told, the challenges, there are solutions for all of them. Implemented solutions for decades. The only task right now for marine industry is to take that knowledge, scale it up, adapt to the marine industry, and use it to reduce the greenhouse gas emissions. So don't be put off by the challenges. Be aware of the challenges, know that such challenges exist, and also know that the solutions are also existed, but there is a lot of innovation still needed to bring those solutions to our marine industry, maybe a lot of optimization to be done from a techno-economic aspect. But once it is all done, hydrogen is one of the best solutions to reduce the greenhouse gas emissions for marine. Thank you so much. I'll take any questions.
Insightful information on alternative fuels. I would like to invite Shaukat, Captain Shaukat, and Captain Mahendra Basin. Please come on stage and present the memento.
Captain Basin, you want to say something, sir?
You know, the time will be too short if I have to start speaking about Padmini. But let me take a minute or so. It was the month of Feb when we reached out to her. There was an article in Economic Times, and it had a mention that a girl from Guntur, the girl from Guntur, ex-ISRO lady, has written the world's first-class rules for hydrogen ships. And then just, I think, it went on viral, then Shaukat, Kaushik Seal is sitting here, and we just got talking. Okay, how to get Padmini to India. But as she also mentioned, I'm only been 2 years in shipping. But let me say a few things about you. Whatever I remember, I didn't prepare anything. Starting from Bits Pilani, please correct me wherever I go wrong. With the age, you forget. Bits Pilani, then you went for Tata as a scientist. You worked on a ISRO for a cryogenic science, as well as for the space science. Satish Dhawan Center for about 7 to 8 years. Because I will tell you from where I got the information. She knows from where I got. My daughter is working with her. Let me confess. They are together working in Southampton. And because she keeps sending me things. And then when the rules came about writing the hydrogen rule, Lloyds has never done it before. That was also the first for the Lloyds to write a rules for the hydrogen ship. And she was the person who, along with her team, and she wrote it. And we were all discussing, Kaushik, Shaukat and us, how to name her. And Padmini, we were thinking of Iron Lady, Indian Lady, so many names came. And then Tim said, Hydrogen Lady. So big round of applause for the Hydrogen Lady from India. Thank you.
I have a short story to share about how proud I am to host Padmini today. 2 years back when we were hosting Tim, this is Tim's 4th year running. 2 years back, I had finished Tim in one of the hotels and I'd gone back. I was having a good night's sleep, and then suddenly in the early morning, 4 o'clock, and it was 4 o'clock. I got a message from somebody global. I don't want to take name. Said, "कितने आदमी थे?" कितने आदमी थे का मतलब क्या है? तो शोले का dialogue है. So and then and they said 10 आदमी थे speakers, and there was no lady speaker. In fact, she asked me, "Why don't you have a speaker? Why didn't you have a lady speaker?" And then I came back, I sort of did my research, and there was absolutely no lady speaking about IT. I mean, so many people here with so many companies representation. How many companies do have IT, ladies in the IT team? Anybody? See? No. It's a point to ponder. And I'm so proud of you that finally we found one, and the best out of that. So, Padmini, thank you so much, the lady to talk about technology.
We all are proud.
We all are proud.